this video, we show our recent work on an optimization framework for estimation control of a spatiotemporal process using mobile sensors and actuators. This research is motivated by large-scale spatiotemporal processes like harmful algal plumes, oil spills, and wetland fire. The monitoring and containment of these processes have relied heavily on human operators, which can be inefficient and dangerous. Our solution is to deploy mobile robots for these dangerous tasks, following a cooperative framework for the mobile sensors and actuators to conduct estimation control of the large-scale spatiotemporal processes. The framework is implemented in a receding horizon fashion. The core is an optimization problem. We feed the problem with the initial locations of the vehicles and the initial state of the process, and it will solve for the actuator's guidance and actuation. Then the guidance will steer the vehicles to move according to the dynamics. Now the actuators can implement the actuation to the process as the vehicles move around. Here, the simulated process is modeled by a partial differential equation, PDE, and specifically a two-dimensional diffusion equation. And then the co-located sensors collect the measurement to innovate the Kalman filter for estimation, which also requires the information of actuation. And finally, the loop is closed such that the vehicle's locations and the estimated state are periodically sent to the optimization problem to solve for the guidance and actuation. The core optimization problem is as follows, which looks for both the actuation and guidance of the vehicles to minimize the magnitude of the PDE while penalizing the aggressive motion. The constraints include the dynamics of the PDE and the mobile agents, and also the bounds on the actuation and speed of the actuators. We demonstrate the framework on an outdoor multi-quadrotor testbed at the Fearless Flight facility. We conducted two experiments with different types of boundary conditions. We showed the trajectories of the quadrotors following the optimal path. The evolution of the spatiotemporal process is shown in the background. In both experiments, the proposed framework can effectively reduce the norm of the process to close to zero compared to the uncontrolled cases. This video shows the experiment. The receding horizon framework plans a 15-second window for the quadrotors to implement the actuation while flying along the optimal trajectories. The animation on the top left shows the impact of the actuators to the process. Now the optimization uses the current process state and the quadrotor's locations to compute the optimal solution for the next 15 seconds. Once a new solution is obtained, the quadrotors will resume flying and conducting the actuation. Thank you.